For a multidimensional function, where the argument is x is a vector, not a number, the first derivative is a vector called gradient, and it has the symbol nabla. And now we need the derivative with respect to each element of the argument vector x. So this is our function. This is not a number now, this is a vector. So the gradient of this function is given by this vector here, and we have the derivative of the function with respect to x1, x2, and so on and so forth until we reach xn, where n is the number of unknowns in our vector x. For the second derivative, we need to take each element of the gradient vector and again take the derivative to each element of the argument vector. Hence, we obtain a matrix, and this is called a Hesse matrix, and it's a matrix of second derivatives given here. Observe that this Hesse matrix is symmetric for reasonable functions that we consider like continuous functions. And using these definitions, we can generalize our Newton algorithm to the multidimensional case. So the one-dimensional case was given by this iteration here, but now it will turn into the multidimensional iteration. So this is not a number now, we're dealing with vectors. So we see here, this is the inverse of the Hesse matrix, and here's the gradient of the function, and these are our vectors. For a minimum, this Hesse matrix must be positive, definite, so all eigenvalues are positive. The problem here is that for the Hesse matrix, we need to compute n squared second derivatives, which can be computational too complex, and then we need to invert this matrix. So what we can do is to make a simplifying assumption that the Hesse matrix can be written as a diagonal matrix with constant values on the diagonal. Observe that this is mostly a very, very crude approximation, but since we have an iteration with many small updates, it can still work. So now we will assume that this Hesse matrix is 1 divided by alpha times the identity. And the best value of alpha depends on how good it approximates the Hesse matrix. Hence, now our iteration will go from this with this inverse of the Hesse matrix gradient, and it will turn with this crude approximation to this one here. So we have x of x new is equal to x old minus alpha times the gradient of the function. And you see now that those are vectors. And this is much simpler to compute than this one here. And this is also called the steepest descent, because the gradient tells us the direction of the steepest descent, or is also called the gradient descent. This is a very important method used in many machine learning applications and on deep learning and so on. We see that the update of x consists only of the gradient scaled by a factor alpha. So in each step, we reduce the value of f of x by moving x in the direction of the gradient. If we make alpha larger, we obtain larger update steps and hence quicker convergence to a minimum, but it may oscillate around the minimum. For smaller alpha, the steps become smaller, but will converge more precisely to the minimum. Because of the update direction along the gradient, this method is also called gradient descent.